Today is our third class, and we're talking about machine learning and how to create a classical machine learning model. We're going to specifically focus on SVM. However, with the same code, you should be able to branch out to other similar classical models. So we're going to talk a bit about SVM, what is fitting, how to train a model using the dataset that we have. First thing is you need to install the need to have GitHub desktop, but you also need to get this code from this link. The link is shared within the group. When you get to GitHub, this repo, you need to click on code and then open with GitHub desktop. And this will let you clone this. I have already this cloned, so I'm just going to give it a different name. And then I'm going to clone. Okay, once you're here, you should also see the open in Visual Studio Code. If you can't see this, it should be saved somewhere in your GitHub folder. So somewhere in Documents, you should have a folder called GitHub, and you will find it in your GitHub folder. So this is SVM and Fitting 2. This is where it will be stored. For me, I will just click Open Visual Studio Code, and it will open right here. So when you open it, there are files that are ready for you. The one we're going to go through first is the machine learning walkthrough. However, the rest are there for you to inspect and look at. There is also a visualized folder where you can inspect some of the other functions more carefully. Um, the first one I'm going to go through is the machine learning walkthrough. What is machine learning and why do we use it? So machine learning is a type of AI that uses data to make decisions without being programmed on how to do it. So rather than writing functions, we're using these models to make the decisions for us. So a model itself is a system that was trained on this data to detect certain patterns. These patterns can be used to perform some kind of prediction on data that it has not seen yet. So models themselves are saved as actual files. They contain all the parameters, all the weights, all the settings that we have trained on, and then they're saved somewhere, and then you load them and you use them to predict something new. They sometimes can be saved as one file. Sometimes it can be multiple files that are working together as one unit. With regular machine learning models, you have to sort of extract the features from your data before you can create your model. So feature engineering is a very hard process. It requires you to have extensive knowledge in the area that you're creating your model from. So if you're making a classical machine learning model, you have to know what you're doing in that field. If you're trying to detect cancer, you have to know something about cancer and you have to know it really, really well. If you're detecting weather patterns, then you also have to be really, really good at detecting weather. If you're if you want to do something in finance, then you have to be some kind of finance expert. You have to know how to extract these features from the data. The other side of this is called deep learning, which we're going to go through in the next lecture. And you find these features automatically using CNN. So they extract these features for you, and then that's how you build the model. This reduces the barrier of entry because you don't have to be an expert in this field for you to make great models. So SVM, this is a support vector machine. This is a kind of model that draws a boundary line between your data. When you look at this, we can see that we have these red crosses right here, and then we have these blue dots on this lower left side, and then we have this very solid black line right in the middle. So this is the decision boundary. This is where we say anything below this threshold is regarded as blue. Everything above this threshold is regarded as red. And these margins right here are they're like margins between this decision boundary. There's nothing that can sort of cross over this. If something goes a little too far, it's still within the boundary. But the thing that is really close to this margin is something that supports this rule. So this circle right here supports this dotted line on this side, and this circle over here on the blue side supports this margin here. If this circle moves closer on this side, then this line will also move closer. So what we're trying to say is all of the features extracted for feature 1 and 2 for blue are on this side. So if there was ever a new unknown circle or a question mark, for example, that came and the question mark was right here, then this will be regarded as a blue dot because it is within this area. And let's say if the question mark was here, then we'd say that this is a red cross because it is within this boundary over here. So this is what SVM does, and there are different kernels that decide this kind of boundary for you. So this is when we're using a linear kernel. When you're using an RBF kernel, it creates a very rounded function. So you get these circular functions. So here we have two sort of boundaries. We have this red boundary over here, and then we have whatever is left outside as the blue boundary. So sometimes, depending on your data, you might need different kernels. The thing with this kind of data, it only works visually if you only have two features because you can plot them on the x-axis, on the y-axis. But for abstraction, this is how it works. When we're talking about images, you will not be able to really view this kind of graph. You just have to think this is what is happening with SVM. So there is a website if you ever want to go through some of this stuff. It is called scikit-learn. And scikit-learn is what we will use in this code for SVM. When you go to this website and you go to user guide, under the heading 1.4 support vector machine, if you click it, it will show you what they are, a description of what it is and what classification is, and specifically the kernels that they're available. So you can see this is the linear kernel that we have. We also have RBF, which is circular. We also have a linear SVC, which is a little bit close to the regular one. We also have polynomial, which does polynomial curves on your data to create the boundaries. So this is scikit-learn. We will use this in our code for this lesson. So what is it when we talk about features? So features are key pieces of data that describe and define it. And anything, especially for images, we're trying to look for things that describe that image. When we say we have a picture of an orange, we're trying to figure out what an orange is. We would say its features are that an orange is round, or that it has tiny holes on its surface. That describes the orange's surface. Or we can say it has the color orange when it's ripe. That means that's the color that defines this orange. Or sometimes it may have a stem from the top on one side. If the example was like a human, we could say that a human has a face, a human has eyes, the human has hair, maybe a human is wearing clothes. Things that describe that object is known as a feature. With HOG, we can attempt to get the gradient of an image, and so we get these kinds of features from the image. And HOG is a histogram kind of process that will take your image and transform it into a gradient of lines. I can show you what HOG is. There's another website we will use in scikit-image. The website is called scikit-image.org, but if you search scikit-image on Google, you will find the page, and underneath documentation, examples, when you scroll down to detection of features and objects in history of oriented gradients, which is HOG, you will see what HOG really does. So here we have an image of an astronaut, and you can see the way it transforms the input image into this gradient kind of based image. So it would take a block of pixels and transform them into like a line of sorts in a different degree. So you can see the way it redraws the whole image into these lines over here. So this is the histogram of oriented gradients. And it, in a way, we can say it extracted some of the features that are required to represent this image. So that is HOG, and we have code for HOG. This code technically comes from the website itself. Right here, underneath this image, we have this code right here. So it takes in the image, it takes the orientations, it takes how many pixels you want to compute by for this gradient, and if you want to visualize the image, it will return the image so you can view it with CV2. So this is the HOG is how we compute it. We're going to go through a 2 by 2 pixel block. What this means is that it will go through every 2 by 2 pixels. So there's 4 pixels in total. The smaller the number is, the longer it will take. The larger the number is, it will take less time, but it will be more quality. So let's do an 8 by 8 first. I'm going to connect this. You can see that it's like a very, I'd say, washed down version of the apple. You can almost see that this is like a very quickly drawn version of the apple. The smaller we get, let's say if we go for 4 by 4, you can see it's getting a little bit more smoother. And if we went for a 2 by 2, we get a really smooth sort of image of this apple. So this is what HOG does. It creates these gradients for you. And we'll use this to for our model, for SVM models, to increase the accuracy. So when you're training a model, we use this word called fitting. Fitting is the process of training a model. When you fit the model, it's like you're trying to cover all of your logic, all of your understanding over your data. So when you're fitting your model, it's like as if you're buying a sweater. You are the data itself, and the model is the sweater. When you're fitting it, you're trying to check if it matches your size, if that data holds on to your logic. So what you're trying to say is if it is too loose, if it's too loose, we say it's underfitting. It does not represent all of the data. If it's too tight, it is overfitting. It is too strict and needs exact data to match to your predictions. And if it's just right, then it fits perfectly. It will perfectly generalize all of your data and create good predictions. So when you're fitting an image, we're still looking at plots of graphs right here. We can say it is underfitting if it does not really represent your data very well. If it's just right, it tries to go through your data sort of evenly, like not exactly, but just really well. If it's overfitting, it's trying to go through as many plots as possible. So it's getting very, very strict, very, very tight. This is for regression. We're currently doing classification. So this is the way it's trying to divide these two classes, the red circles and the blue circles. You can see this is underfitting because it's not really dividing it very well. You can see there's still blue over here. This is trying really, really well to divide the sections. Even though there are two on this side, this is more than enough. But this is overfitting. It's trying to divide it way too well. So it's not really representing your data very well. We will learn about these curves later on in deep learning next week, so you can understand what these graphs mean, especially when you're underfitting and when you're overfitting. So this is the walkthrough. Please go through it slowly. You can run this code as many times as you like, so you can understand HOG. What we're doing today is we're trying to train using SVM. So the first thing you do need is your data set. If you're using my data set, the one with fruits, the data will already be there. If you're using your own data set, then you'll have to replace the names, the folders, all of your data, and you'll also have to replace the text itself, the path to your data set. So I have a folder called datasets, which is right there. I also have a path for images where I have some test images to test later on. And I also have a folder for models, which I will save all of my model files and my class name files. So in here, we have this file called svm training.ipymb. This is my Jupyter file. I also have a prediction file, which we'll go through later, and we also have an augmentation file, which we'll use for augmentation. So we're going to be using scikit-learn, which is the package just talked about for creating machine learning models. And we're going to use scikit-image to be able to extract the HOGs. There are also two more packages. There's joblib and there is numpy. Joblib is used to save and load objects from Python and save them, let's say, to your file disk, or load them from disk and put them back into your Python code. It is a very simple library and there are only two functions. We will discuss them. There's one called joblib dump that will save it to disk, and then there is joblib.load, which will load your model. Um, NumPy is a matrix library. It is used to convert all of your arrays into matrices to make your code more performant. If you use Python as it is for your loops and your machine learning processes, you'll find that your code is very, very slow. NumPy has features that will be able to multiply or add all of your matrices really, really quickly. But all in all, they're just really fancy versions of arrays. An array looks something like this. For example, if I say I have an array, we have enclosed brackets, and then we have all of our data inside. So if I have the numbers 1, 2, and 3, we're saying that we have a one-dimensional array because there's only one set of brackets. So this is a normal array. And if I print this, let me just play this. So it installs. Okay. If I play this, you will see I just have the numbers 1, 2, and 3. And if I turn this into a NumPy array equals to NumPy array. So I haven't really imported NumPy, so let me import it here, just so I can show you. Import NumPy. When I run this and I play this, it will create a NumPy array. Let me call it, wait, sorry, as np np dot array. And then I'm going to print it just to show you what it is. When I play this, we have the same thing. It's just that it's a matrix-like version of this array. So you can see kind of remove the commas. It's just, but it's almost the same thing. So this is a one-dimensional version of an array. And similarly, it can make matrices out of this. So if I was trying to make a matrix, I would, let's say, copy this, put a comma, and then I would keep 4, 5, and 6, and then I would make new brackets outside of this. So this creates this as the first row and this as the second row. And the columns are going 1, 2, 3. So now when I play this, you can see that this is a normal array. It prints it normally, but this one prints it as a matrix. So you can see this is column 1, this is column 2, and this is column 3. So NumPy is just used to make matrices and make all of your mathematical processes a little bit faster, more performant. So I'm just going to delete this code. This is not very, very important for now. So we're going to be using NumPy for that. So we have the four things we're going to use: scikit-learn, joblib, NumPy, and scikit-image. So we import them here, and then we say that I want my image size to be a certain size. So I have mine at 64 by 64. This is what I pre-process them as. If you have them as 32 by 32, change that to that. If you have 128 by 128, also change them to the way you have pre-processed your images. Now I'm going to start with the processed fruit data set. This is before it's augmented so that we can see the accuracy. And I'm going to start off with these three variables: the data, its labels, and the class names. Don't worry too much about this for loop. What it does is it goes through your data set and loads the images. So all of this, all the way from here, this is all just a for loop for loading your images. And it will check if there are images. If you have different images type, you can add them there. This code should be very, very familiar. You are trying to read your image in grayscale and you're trying to resize it. And then this is also should look familiar. We're trying to extract the features from the image itself as an HOG. And then we're trying to append those features. So all those features will go into this array, these brackets over here. And then the labels as well will also go into this one, and the class names will also go into the class names. So let's talk about these three things. What is data, what is labels, and what is class names? Data is the way the images are stored, the colors, all of the pixels as one thing. So let me just make a comment here. Data will be your actual images in pixels. And then we have labels. Labels are the labels of your images, but in number form. So let me just write this down and explain it. In number form. For example, in your folders right now, in datasets, in processed fruits, we have three specific class names. We have apple, we have banana, and we have orange. What all of these codes do, especially machine learning code, when they load your data and they're trying to find labels for your data, especially if they're in folders, they will first alphabetize all of your label names, your class names. So we have apple, we have banana, and we have orange. If, for example, we had a different fruit, let's say we had kiwi, we know that kiwi is between B and O, so kiwi would be right here. So it will make it in alphabetical order. Now we only have three, and it will give each class name a number. So the first one is always 0. The second one will be 1. It will go up, and then we'll add 1. So this will be 2. So all of these labels will be kept inside of this array. And then we have class names. Class names are your actual class names. So class names. So your actual class names are these ones. So you'd actually have apple, banana, and orange. And they will be saved together like this. So this is the array will be just these three. So let's say we run this and we want to see what happens. Also, we're trying to turn them into NumPy arrays. So what I'm going to do is I'm just going to log all three of these. I'm going to put them here, print data. Data is going to be really, really large. So I'm just going to play it once and then remove it so you can see it. So this is the data. This is all of our, the pixels of our images. And then I'm going to show you the labels. Let me get rid of this. These are labels. We have all of the apples. Then we have all of the bananas. And then we have all of the oranges. And lastly, we have class names. And we only have three class names. So these are the class names we kept here: apple, banana, and orange. So this is what we have so far. We have loaded all our data. What we want to do next is we want to um, uh, split our data and then train it. So I'm going to talk through this, even though the code is already written. I'm going to explain what it means. So first thing, we're going to import this package called SVM from sklearn. This is our model. Whenever you're trying to find a specific model, most likely it will be in this package sklearn. I will show you exactly how to find these models later on and how to use them in your code. However, it will follow the same process. You will still need to first load your data. Once you load your data, this is the part where you're picking your model. So this is the picking your model type or architecture. And then this is going to be your third step. So this is 2, this is 3. You're going to have to find a way to split your data. And then your fourth part is going to be to train your model. So in this will be model. And then later on, you're going to need to perform some kind of metric assessment. And then once you figure out how your model is, how well it does, the final step is to always save your model. So you always follow this kind of step. Most of the times, number 5 and number 6 doesn't change so much. Your code will most likely look the same. However, the training may look different, and this part may also look different when you're picking your model type and architecture. So here we're picking an SVM architecture, an SVM type. We're saying that we want to train our test split. So what we're doing is we have all of our data, but we don't want to use all of it just for training. We want to portion some of it so that some of it can be used for testing. So when you're doing this, you sort of create a ratio, how much you want for training and how much you want for testing. If you're just training your model by itself with all of your data, then you don't really know how well it performs on data it has not seen. You need to figure out a way to test. And the best way is to use data from the same distribution first. So using data from the same distribution, it means that it comes from the same folder, it's the same type. So here we're trying to split the data. There is the training data and we have the training labels. You know what data is, you know what labels are. We're also splitting from test data and we're splitting the test labels. And this function will let you input your data in labels. These are NumPy arrays. It will let you decide the test size as well as the random state. So what is this test size? So the test size is how much of each side you want. So if I have an 80-20 ratio, what I'm saying is I have 80% of training and 20% of testing. And this is always in percentage. So this is this side and this side, and it has to total 100%. So this is the same as saying we have 0 0.8 for testing, and we have 0. Let's make this TRA, and then we have 0 0.2 for testing. So this is the 0 0.2 for testing. That means we have 20% for testing and 80% for training. You can pick different ratios. You can say that I want 70% for training and 30% for testing. You can go even lower. You can say maybe I have enough for training. I have 50 and I have 50. So this will translate to 0 0.7 and 0 0.3, and this will translate to 0 0.5 and 0 0.5. Now, why would you really pick these kinds of ratios? You only pick these kinds of ratios depending on how much data you have. If you don't have enough data, you should go for a very even split. Let's say you have 100 images. You might need to use this split. So the less data you have, you should go for a very high range split. If you have medium-sized data, you should go for a very kind of comfortable split. So between 70 and 80. So this is if you have medium-sized data sets. If you have really high data sets, for example, you have 10,000, 20,000, 1 million images, you should go for a really small amount of testing size. So let's say I had 1 million images, I might go for a 95% and a 5% testing because I don't want too many for testing. I want to use most of my images for training to improve my model. So in this example, if we had 0.95 by 0.05, this is only if you have a lot of data. So a really large data set. So this is a reason why you pick the different ratios. You should always experiment though with your ratios, try different things, see what it does to your models. So we have already split our data. What's the next step? Let's play this. It has split our data. Now we're going to train the model. So this is called CLF. I'm going to rename this model so that it's easier to read. So this SVM package will select the SVC, the support vector classifier, and it will use the linear kernel, so it divides it with straight lines. It will then try to fit, which is a form of training the model. So we're fitting using the training data and the training labels. When you're training machine learning models, they will not take very, very long because they're very, very simple. They will just take all the features that you have given them and create this boundary for you. When you play this, it takes almost like a fraction of a second. So it's very, very quick. You can see right here, it only took, I think it doesn't want to show anymore, it took 100 milliseconds. It was very, very quick. So after this is done, what we want to do is we want to perform metric assessment. We're going to import something called accuracy score from sklearn metrics. You will reuse this package a lot if you're creating machine learning models with sklearn. And to test the accuracy, we're trying to use the model that we just created. We're going to call the predict function, and we're going to pass in the test data that we split over here. This is the test data that we split. And then we want to show the accuracy by using the accuracy function. And we're going to test against the test labels if the test predictions were correct. So these test predictions are the numbers. If you want to see the comparison, I think we're going to show the comparison. Print test prediction. I'm going to copy these. And then I'm going to call test labels underneath so you can see them side by side. So when we run this, we can see these are the test predictions. This is what your model said, and this is the true actual label. So it predicted 2, but the correct answer was supposed to be 0. And then it did the same thing and it continued in that fashion. So because this is what your predictions were and this is what the real values are, it gives you an accuracy of how well your model is predicting against your data. So currently it's giving us a 0.58%. And this ratio, this decimal point in percentage will be 58%. So we're saying for our first run, we got 58.18%. And technically, that's not very good. Whenever your model is less than 50, then we're saying that your model is not really learning. It's not getting all of the features from your data. It's not performing very well. So this is not performing very well. Whenever your model is exactly 50, we're saying your model is guessing. It's not even sure what it's doing. So this is also a bad value. Whenever you have anything under 50 or equaling to 50, your model is not really doing very well. What you need is to try and hit values from 70% going upwards. So if your model is sort of trying to hit 70% or more, then we're saying that your model is really trying now to learn. It's really trying to pick up data. But you should always try to reach really high values like 90% or 95% so that you're sure your model is predicting well on your data. So far we're on 58%. What we're trying to do is we're trying to increase this accuracy percent. Um, to increase your accuracy, there are many, many ways to do it. But the first thing is to ensure you have enough data. Currently, we're using processed fruit dataset, which does not have a lot of images. What we need to do is augment it. Augmentation, what it does is it increases the size of your dataset. So when we had, let's say, 200 images in our processed dataset, what we did was we multiplied them by creating new images with different designs on them, like different color brightnesses, different crops, different, let's say, ranges of color. And this creates a new image from the one you have. And in a way, you can augment your dataset as much as you like. However, you have to be careful how much you augment it. I'm going to use a very simple augmentation. We're using augmentations. You should also become comfortable with this from the last lesson. What we do is we take the dataset and we create a new one called augmented fruit dataset. And what this will do is it will create a composition of what you want to try to do it on it. So I'm going to flip my image. I'm going to perform some kind of brightness contrast, and I'm also going to try to rotate it. And currently, I don't want too many augmentations. I just want a simple version of this augmentation. It will go through my process fruit dataset, read the image, and then perform the transform, and then save it. So currently, I already have an augmentation done. You can see this is an augmented version of my image. Some of them are rotated, some of them are darker, some of them are lighter. Now, inside our training, I'm going to change this to augmented fruit data set just to see what that does to my accuracy. I'm going to replay the blocks. I'm going to play this, and then I'm going to rerun this. Now we see that we have 69.09%. So I have my second run as 69.09%. So this was without augmentation. This is now with augmentation. Now, augmentation can do good things, but it can also do harm. If you augment too much, it may have the opposite effect. It may have a good effect. You don't know how much is too much. So you always have to test how much is too much. This script lets you augment as much time as you like. So let's say I want to augment this 15 times per image. I'm going to play my script. I'm going to play this block. I'm going to perform this. Let's confirm this actually ran. I think number of augmentations. Okay, let's run it one more time just so we have more images. Okay, let's say we have 825 new images in this augmented fruit data set. Let's see how it does with our current setup. So I'm going to replay it from here. I'm going to reload my images. I'm going to replay this. On running this time, it seemed to be a good thing. It says that because I augmented this many times, third run, I have 73.63%. This is with more augmentation. So let's try and do it more times. Let's see if it has a bad effect. Let's keep playing this, see if it does something wrong. Okay, let's play from here. Okay, so it was 73%, but now it's trying to drop. So the more augmentation you do, it does not mean that your model will get better. It just means that it's performing. So don't do too much augmentation, just try and sort of stick with enough. You can use these scripts so you can test your own data set to see if they perform better. For me, I'm just going to delete this folder and just do it once because I don't think we need too much. Let me just set this to 1 and replay everything. Okay, so this is the original one we have. And I'm going to continue with my third run of augmentation at 73.63%. So let's say my model is still not very good. I'm not happy with 73%. I want to see what other ways I can increase my accuracy. So another way you can increase your accuracy is to change your ratio or between testing and training. Different ratios can do different things. You just have to experiment and see what happens. It may improve it, it may decrease the accuracy, but you should always test and see what happens. So I'm going to test with 0.3, giving us a 70-30% testing. I'm going to, actually, let me start from the beginning. I'm going to replay the first block. I'm going to replay this. I'm going to replay it again, and I'm going to replay this again. It's giving me a 77.57% testing with a different ratio. So all of these were under an 80%, 20% ratio. And now we have a 70% to 30% ratio. And whenever you rerun this code, let me just write this down before it disappears. Fourth run. This is 77.57%. This is ratio change. Whenever you rerun this code, and you replay everything, you'll see that you get the exact same value every time with your changes. And this is because of this last thing called random state. What the random state does is it gives you a version of the split that is randomly the same every time you run it. So at random state 42, it means when it splits, all the images on this one split is the same as the other. If we were to change this number, you'd see that this version changes. When you're actually running this, especially for your papers, when you're publishing, you should always have a random state that you stick to. So let's say if I change this to 12, and then I play it this time. Let me start from the beginning. Play, 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 play. You'll see that this number changes. It became 68.48%. So this version of this split made the model worse. If I go back to 42, you'll see that we're back to the 75.57%. So whenever you're training and you want to stick to a certain experiment, you can set your random state to a certain value so that you're sure this is the way you want it to work. So currently we're on the seventh run. I think it's going well, but maybe I want to change my test size. Let me see if it does any difference if I keep a 0.5% split. So I'm going to replay everything. And now it just gives me 68.72, so it did not do much difference. So I don't think this is important anymore. I think 0.5 is too much, so I'm going to go back to 0.3. I think that's enough for me. So those are some of the ways you can increase your accuracy. However, the last one for SVC specifically is to change the kernel. We had these kernel types over here. We have linear, we have this SVC linear, we have RBF, and we also have polynomial. You can try the different ones to see what they do. We can try with RBF and polynomial to see what they'll do to our accuracy. So let me try RBF first. I'm going to play again. Play, 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 play. Now when we run this, let me remove these values so it's easier to see. When we run this, we get 78%. So that is another increase from 75. I'm going to put this as my fifth run. I'm going to say 78.18%. And this was because of changing the kernel, RBF. So my fifth run gave me 78.18%. I'm going to try and change this to a different kernel, let's say polynomial, which is poly, and I'm going to replay everything to see if it had an effect. I'm going to play and then play this again. When I play this, I get 81.8%, which is good. So I know that on my sixth run, I got 81.8%, and that was changing to polynomial. So this polynomial made it a little bit better. So these are some of the ways that you can increase your accuracy. You can always try different things to see what happens. I did change this to polynomial, but then that means I also have other factors to consider. Maybe with an 80-20% split and polynomial change, that might give me a better result. So test out different experiments, see what happens to your model. You can always increase it by trying out different things. It's always trial and error. Nothing is set in stone. You can always find new ways to increase your model accuracy. So after you have trained your model, you have fitted it. Let's say you're happy. Let's say I'm happy with my 81% at the moment. I can save my model. So my model is called model. I'm going to import joblib, and there's a function called dump. So joblib.dump. The model name is called model, and I want to save it in models, which is this folder. And I want to save it as SVM underscore model joblib. So these joblib files are just Python objects that can be exported and imported back into Python. I also want to export the class names, which are the apple, banana, and orange. And I want to export them as class underscore names dot joblib. When I play this, I will have these models in here, and then I can use these for prediction. There is a last script, this Jupyter notebook, for testing. So for testing, I have my images. There's a folder called test, and then I have a file called banana test.png, which is currently a banana image. I also have another banana, which is yellow. I have this file called images-2, which is an orange. And I also have another one called orange underscore 13. So these are my test images. You can always drag your own images in here for you to test. I am going to start with this one to see how well my model did. Now, whenever you're testing, you're also trying to visually see if your model is performing correctly. Sometimes you can have an accuracy of 81%, but that does not mean that your model is perfect or that it has great accuracy or that this accuracy is real. There are other metrics that we will go through in another video, and these metrics will help you analyze your model and test if your model is actually saying the correct thing. So sometimes you do have a really high accuracy, but your model is actually overfitting to your data. So it's only 81% accurate, but on this specific data, not on images it has not seen before, images from Google or images from Pinterest or images from other data sets. So this accuracy just defines your accuracy on your data set. So when we're predicting, we're trying to see if our model is okay. If it's not okay, it means you have to go back to the drawing board, you have to retrain and try again. So I'm going to play this and then I'm going to see what happens. When I play this, it says that I have a prediction index of 1. So apple was 0, banana was 1, orange was 2. So I get 1, and from my class names, if I keep that 1, I get banana. I'm going to try a different image. I'm going to try images2.jpeg. When I play this, it says orange. Image 2 was exactly an orange. If I try just banana.png, you'll see it also says banana. And the last one is orange underscore 30. So this is orange underscore 30. When I play this, it gives me orange. So we know that our 81% is really good, but you should always try and test different images, especially ones from the web, see ones that have maybe less lighting, see how they perform. If your model is performing really well, that means it's good. If it's underperforming, then you always have to go back to this and retrain. There is another video for other metrics that will come out so that if you're trying to make classical models, you can compare these metrics to the accuracy to see if your model is not overfitting to your data. However, if you have gotten this far, then you might need to practice a lot more. What you should do is maybe try out different data sets, try out different things, try predicting different things, try creating different types of models. Um, Over here in SVM training, there will also be another video for importing different types of models, like KNNs and so on, so that you can use them to create different types of models and then compare your models against each other. But so far, try and practice with different data sets for SVM, see how they, let's say their accuracies are, see how difficult they are to get really high accuracies. If you get an 80% accuracy on SVM, congratulations, it is not that easy to get, but always aim for a really high accuracy of 90. And because 90% means that your model is performing really, really, really well. And especially if you're publishing, this number is really, really good. The closer you get to 100, it's good, but does not mean that your model is perfect. It is very rare to get 100% accuracy. Don't aim for it. If you get 100% accuracies, a lot of reviewers will always ask you questions. So you have to always have data to back up how you're getting really, really high accuracies. But so far, so good. If anyone has questions, you can always ask them in the group. I will release the other two videos for people who want to train with different models, um, as well as the metrics for other than accuracy for the other models for classical training.